Video in section 9.7, which is about approximating functions with Taylor polynomials. So in this video we're going to look at a complex topic, perhaps one of the most complex topics in this course, but pretty important, and also from what I've been told, quite tested on the AP exam. We'll see if that's true when we begin to look at AP responses, but. Basically, this is the Lagrange error bound, but first let's just talk about what we know about Taylor polynomials so far. So if we're trying to create a Taylor polynomial to approximate a function, we can talk about it like this, right? So if we're trying to approximate the function f of x, we create some order of Taylor polynomial. Remember, that depends on how much computing time we have and all kinds of factors. But we're going to create some order of Taylor polynomial, the nth order here. And of course, that's not going to exactly approximate the function. We've seen a couple problems now where we start to see that, oh yeah, it's not exactly it, but usually it's a pretty good job by the time you get out to like the fifth order approximator or something. There's going to be some little amount left, so let's just call what is left that would make it exactly equal the remainder. So we'll also subscript that with n because that's going to depend on what polynomial we create, the fifth order, the seventh order, how many terms are in our Taylor approximator. Okay? So, of course, you can use some algebra and solve for that remainder now so that we can begin to think about that remainder. And that's what we're going to do in this last video, is dissect the remainder. So, of course, if you subtract the Taylor polynomial to the other side, you get this. And then if you take an absolute value on both sides, you can begin to talk about the error associated with the approximation that you've created, okay? So if you take the absolute value of the actual function minus the polynomial approximator you've created, you get the how much error is in your approximation. So that's just the definition. So this is called Taylor's theorem. The book calls it Taylor's theorem. What's really important about it is, and I'll put it in red and star it, is this part down here. This is called the Lagrange error bound, and this is what I've been told is on the AP exam a lot. And even if it's not on the AP exam, it's something I've seen a lot in advanced math. Big time important. When I was in Hong Kong, this was one of the things I really had to puzzle over because I hadn't been taught it effectively in college. So a very important idea. We used it a lot, but it's used for all kinds of things. Anyway, so let's look at this theorem. It says if a function f is differentiable through order n plus 1. So in other words, you've got to be fairly differentiable. So if you create like a fourth order, for instance, Taylor polynomial approximation, and you hope to use this theorem, you hope to use the Lagrange error bound down here to think about how much error is in your approximation. The polynomial has to, the function has to be differentiable a lot of times. Remember, sometimes functions stop being differentiable because of a sharp corner or an asymptote or a gap or something like that. So you have to be able to take, if it's fourth order that you're using, you have to be able to take 5 derivatives. Okay. So 5 derivatives for fourth order. So that's basically what this says. In order to be able to use it. So what's it say? It says in an interval I containing C, then for x in I there exists C. Though this is fairly complex. So remember, when we create a Taylor polynomial, we usually have some center, right? The center for which the polynomial converges. And then we have some interval of convergence that is defined. But remember, we always picked a certain center, and then the polynomial did the best job at the center. So what this theorem is saying is that there exists some other value z, so this is something new, this z guy. It's between x and c for each x within that interval. So let's say you have an interval of convergence, and you've picked c equals 2, and your interval has a radius of 2, so it goes out to 4 and back to 0. And that's your interval of convergence from 0 to 4. Then this says for every x that's in that interval, whether your x is right here or wherever, for every x that's in that interval, there's this other value z between x and c, so there's some z right here, such that if you take f of x, then, if you think about what you're trying to approximate, what function you're trying to approximate, f of x, and you add on the and here's your Taylor polynomial, right? This is the Taylor polynomial part. So that part plus this error term, the remainder term, you get that z exists, basically. That's the main key, is that there exists this z. So we'll be seeing what we use that for in a second. But the other part that's key is the reason you needed it to be 5 derivatives for a fourth order polynomial, for instance, is because, can you see the n plus 1 derivative in that remainder error term? And it's the n plus 1 derivative at z and then divided by some constant times x minus c to the n plus 1 power. So you need it to be differentiable one more time in order to get that error term to make this, instead of approximately, an equivalence statement. So now what we're going to do in all of our examples is we're going to pick apart this remainder term and see what we can use it for. Okay? All right. One thing I thought was nice was this little snippet. So it says for n equals 0, what if you're just considering a 0-order Taylor polynomial approximation? This theorem, the Lagrange error-bound Taylor's theorem, is widely applicable, but I thought this was a neat use of it. So it says if you take the 0-order Taylor approximator, then the theorem states that if f is differentiable just once, right, in an interval containing c, then there exists a z between x and c such that the function is exactly equal to, there's your Taylor polynomial, and then this guy is the Lagrange error bound. R sub, in this case, is 0, right, of x. So it's exactly equal to that. And you can see from this, if you rearrange the stuff, that you can solve it like this guy. And if you see, that looks very familiar. So this is like the mean value theorem. So the proof of Taylor's theorem in just this one little part, like a corollary to it, you could prove the mean value theorem. And if you remember what I said in Calc 1, the mean value theorem is a very difficult theorem to actually prove at a high level. So you can imagine the kind of level that you'd need to get to be able to prove and really thoroughly understand Taylor's theorem. So it's a very high level idea. So let's go use it for some stuff. That's the main point in this course. So it says determining the accuracy of an approximation. Of course, I'm betting that's what you were guessing and hoping we'd get to. So how accurate is a Taylor polynomial approximation? So it says, okay, consider the third order polynomial approximator for sine of x. Remember we just did one with cosine and it was just the even terms, so sine is just the odd terms. You can go ahead and verify that if you wanted to. I'm not going to this time. Okay? So, let's see. So you use Taylor's theorem to approximate sine of 0.01 with that guy, and then talk about how much error is in it, basically, okay? So sine of x is going to be equal to, this part is the Taylor polynomial, and if we use Taylor's theorem, we say, well, it's exactly equal to that plus the Lagrange error bound, r sub 3, okay? So r sub 3, now we can think about exactly what that is. Well, we're going to go one more derivative, so the fourth derivative of z divided by that 4 factorial times x to the fourth. So this kind of makes sense. The only thing that's really interesting now is what is this thing? That thing is going to tell us about how much error we have, basically. So now we've got exactly equal, not approximately like we'd have had in all of our previous problems. So a part of the theorem was, remember, it said that z, this z guy, had to be in a special spot. Let's go back and look real quick. So remember, it said z had to be between the center of the interval and whatever x value you're interested in. So let's go back to where we were and see where z could be now. So the center of the interval that we created was 0, right? The sine of x is this polynomial if you consider it as 0. So there's c. And then the x value we were interested in when we did this was, of course, 0.01. So z's got to be between those two things. So now let's see what happens. We'll plug it back in. So sine of 0.01, we're just plugging that x value into the function again. And we get 0.01 here, 0.01 here. Notice that this is approximate because we don't have this term on there, right? So let's just see. We get that. So that will be the Taylor polynomial approximation third order that we get. So now let's look at the Lagrange error bound part of that, okay? Let me clean this up a little bit. Okay, so because the fourth order derivative of z equals sine of z, is that true? Let's go up here and look. So if we took the fourth order derivative, what would it be? So sine's derivative would be cosine, right? Let's just go in terms of x. The derivative of that would be negative sine. The derivative of that would be, what, negative cosine. So that would be first derivative, second derivative, third derivative, fourth derivative would be negative, negative, so back to sine. So that's why they're saying this, right? So because that's true, it follows that the Lagrange error bound can be bounded. So they're going to say that that term up here, this whole piece, can be bounded by something. So they're saying, well, of course it's bigger than 0. That makes sense. This is just getting bigger and bigger as we go. But now they're plugging 0.1 into that. Can you see that? So they're plugging 0.1 in for x right there. Can you see that? It's going in for that x value right there. And we've established that f, we just did this is the sine of z, so that's no big deal. So now instead of saying it's equal to something, look, they're bounding it. So they're trying to get like the most error there could possibly be. So this stayed the same, and 0.01 to the fourth power is this guy right here. So where did the sine of z go? Well, think about the sine of z. Remember, the sine is a sine wave, so it goes like this, right? What's the highest it ever reaches? 1. So in other words, that's less than 1 times that thing divided by that 4 factorial. Does that make sense? Because the sine could be at most 1, so we're going to bound it with a 1 there, and they didn't really write it, right? Okay, so then you just see what that value is, and this is what you've got. So in other words, this whole big term up here, this whole big term can be at most this value. So I'm going to circle it in red. So that tells us basically everything we might want, almost everything we might want to know about how accurate our approximation is. So our approximation, which was this guy in green right here, that's our lowest thing it could be. And how accurate is our guy? Well, this gave us a measure. So the lowest it could be is this, and then the most it could be is that plus this. So that's the value that we're looking for, sine of 0.01, has to be between that lower bound and this upper bound. It's somewhere in between there, and that shows that even though we only did a third order approximator, it looks like it's pretty darn accurate, right? It's the same value up until the what? The last decimal place there. What is that? 1, 2, 3, 4, 5, 6th decimal place. So that's 100,000th place. So pretty accurate. All right, one more example. So this time, let's talk about how if we needed it to be exactly so precise, we wanted it to be just like that, so that we didn't waste any computing time, and we didn't waste we just needed it to be exactly a certain amount. So this one says, make it so that the error is less than 0.01. So that's our whole goal. Keep that in mind the whole time. So this time we're going to do it with the natural log of 1.2, and we're going to expand it, of course, about 1 to get to there. Okay? So first it says, think about the n+1 derivative of natural log of x. So they're saying here it is. Should we look at that real quick? The first derivative, let's just see what that is. The first derivative of natural log is 1 over x, right? So the second derivative is -1 over x squared, right? The third derivative would be +1 over x cubed, right? So from that, can we buy this statement that they're finding here? Remember, if you ever need to find the n+1 derivative, you just do this and you search for a pattern. So you can see it's alternating. That's why it's got -1 to the n. You can see that this guy keeps getting bigger, so the third derivative has the third place here. So if they want n+1, this has got to be n+1. You see that? Ooh, n factorial. Why do we need n factorial? I don't see that. Oh, I think I made a mistake in my derivatives. Look at this. So when we did this, it would be go to there, right? And then -1x squared, wouldn't it be a a +2 up here? And then the next one we'd have -3 times 2, so it'd be -6. So that's why that's an n factorial right there. Okay, so I buy what they said. Okay, so they took the nth order n+1 order derivative. Why on earth would they want to do that? Well, if we go back and look at the theorem, of course, erase all this junk. Of course they did that so that they could start thinking about this top part right here, right? Okay. So let's see what they do now. So then they said, okay, using Taylor's theorem, you know that the remainder of 1.2 is given by, so then they use the whole thing, right? So we go back to the theorem. They used the whole thing, so they went and grabbed that whole part, and they just started looking at it. So this is what we just did up there. We'll use it in a second. Then they said the n+1 factorial, and then they put 1.2 actually in for like x in the function. And then they said, okay, that's equal to something else. So this part is all this guy up here, right? So it looks like they dropped that in here. Let's see. So it's of z, right? So that should be a z to the n+1. Got it. N factorial. Got it. -1 to the n. Oh, absolute value. Got rid of that part, right? And then this part is 0.2 to the n+1. There we go. Everything's there. All right, let's see what else we've got. So now they took this and reduced it. I think n factorial over n+1 factorial reduces to n+1, right? This part's on top. Z plus z to the n+1 is on the bottom. All right, so in Taylor's theorem, remember that this guy is the value of this z right here is between the interval center c, right? We said c equals 1, and our x value, which we're thinking about as 1.2. So that's what z has to be. So it says in that interval, provided that z is between 1 and 1.2, this whole thing is less than this. So why is this guy less than this? I like to write that out. So let me extend the page a little bit, and let's write that out. So we'll come back up to this. So remember, it's claiming that this guy is less than this guy, provided that that's what z is going on. So let's write that out. So that says 0.2 to the n+1 over z to the n+1 times n+1 is less than 0.2 to the n+1 over n+1. So if we start like crossing out things, we can get closer, right? So these are both on both sides. This is on both sides. So what's this statement really saying? It's really at its heart saying that 1 over n+1, z to the n+1, is less than 1 equals. It's saying it's less than, right? So that's the claim that they're making. Is that true so long as z is in this interval? I think so. If z was exactly equal to 1, it wouldn't be less than, right? It would be perfectly equal, but see how this doesn't have the equals down there? As soon as z is like slightly bigger, then this thing is going to be slightly bigger, which means the fraction is going to be slightly smaller, right, than it was to begin with. So yeah, I think that this statement they're making, even though it's a little bit out of left field, it does make sense. So that's definitely true. You could actually verify it with a bunch of values and try some things, but I think it definitely makes sense. Okay, so then they're saying, look at that guy. Our whole goal in the problem, the whole goal was to make the error be less than 1,000th. So they said, okay, that is the error term, right? We took the error term, simplified it down to this guy, and now make that less than 1,000 and solve. So it looks like this is 1,000th. So it looks like they multiplied that 1,000 up to that side. Maybe we should do that down here too. So then we've got the 1,000 on that side, and less than. And they're going to multiply the n plus 1 up to this side. And then 0.2, isn't that 1/5? So they're dividing by 1/5 the n plus 1 on this side. So that says 1,000 is less than, and if you're dividing by a fraction, you can use the reciprocal. 1 to any power is 1, so really all we've got left is n plus 1, and this 5 gets flipped up, and it's to the n plus 1. We don't even have to worry about that 1, because it's just 1. So that's where this statement came from. So then they said, okay, try some values of n. So remember, n, what is n here? N is the order of the polynomial that you're going to end up creating. So they're saying, okay, try some values. Do you need to do a second order Taylor polynomial with 2 terms, or a third order with 3 terms, or what? So they said just pick some trial and error, right? Trial and error. So they started with, it looks like n equals 3. Well, I don't know if that's what they started with, but they said n equals 3 satisfies the inequality. Let's see. So for n equals 3, we get 1,000. Put some dots. 1,000 is less than 4 times 5 to the 4th power. So that's 4 times, I think 5 to the 4th power is 625. So yeah, 1,000 is definitely less than that. How about for n equals 2? Maybe we could get away with just a second order polynomial. That would be nice. So 1,000, is that less than 3 times 5 to the 3rd? What is that? 5 to the 3rd is $1.25, right? So 3 times 125 is 1,000. Less than that? Nah, I think that's only like 375, so nope. N equals 2 will not work. Looks like n equals 3 is the cheapest Taylor polynomial we can get away with. So if we do ln of x, third order polynomial, we get the desired accuracy of 0.001. Okay? Hope you found this useful. I think it's pretty darn important stuff. So the next video, we'll start looking at actual Taylor series. See you then.